So welcome everybody, and it's my pleasure today to have Sam Hindson from SDU in Denmark telling us about WRT invariant as finite-dimensional integrals.
Wonderful. Well, good morning, everyone. Thank you to the organizers for inviting me, and thank you for all showing up. I know there's a bit of confusion about times, but it's not as early as originally said. But either way, I'm here to tell you about WRT invariants as finite-dimensional integrals. This is ongoing work with my two supervisors back at Denmark, Yoon Andersen and William Mistegård. And well, I'll begin with a little bit of background on sort of the protagonists of our story, and that sort of starts around the late 80s, where as we saw in Blanchet's talk last week, as he talked about, there was this flurry of activity and sort of the birth of this field, quantum topology. And in particular, I'll draw attention to this construction by Witten from 1989. So what Witten did was he considered some closed-oriented three-manifold M together with a framed-oriented link inside of M. We'll denote the trivial SU2 bundle over this manifold by B. And then for some non-negative integer k, you can define some label set, which is really just some set of numbers 1 up to k plus 1, which Witten takes as to be the isomorphism classes of highest weight reducible representations of SU2 up to of level not greater than k. And together with a coloring of this link, that's essentially just saying for each component of the link, assign it one of these irreducible representations of SU2. And so you throw all of that together in a pot, as Witten did, and what he showed was that you can construct a topological invariant for this triple, for M, L, and the coloring. Well, not just one, an entire family, one for every such non-negative integer. And that comes in the form of this path integral, which is performed over the space of SU2 connections on this bundle, modulo gauge transformations. We have an action over here that's weighted by the level k, well, the Chern-Simons invariant of your equivalence class of your connection is defined like this. It's an element of R mod Z in the case of SU2. Gauge transformations sort of leave this ambiguity, so you have to end up quotienting out by the integers. And together with this is a Wilson line, a bunch of Wilson line insertions, right? So it's essentially saying for every link in your manifold, take the representation that you colored that link by, trace your connection around that link, form a holonomy around it in this representation, and then take the trace of it. And of course, here's this path integral measure, which, if you're like me, you sort of hold at arm's length and go, path integrals, I'm not so comfortable with that. But really, the results did speak for themselves, using some some very elegant arguments in quantum field theory. What Witten did was showed that this allows you to recover sort of the ordinary Jones polynomial skein relations. Yes? Okay. I'll stand to the side. Yes, one recovers the skein relations that sort of define the Jones polynomial, and in so doing, allows us to say that this is something of an intrinsically three-dimensional sort of interpretation of the Jones polynomial. And well, a generalization as well, because we've also got these colorings by representations of SU2. But not only that, it also works for links in arbitrary three manifolds. And well, what it actually allows you to do is, if your link is in some other weird three manifold, it allows you to reduce computations of this quantity back down to links in the three sphere, where we are very familiar with this, where this is just the standard Jones polynomial, of course. But there's if you're not too comfortable with part integrals, and you might say, oh, I want some other tool to be able to do this, then, well, you're not alone. And so there was this idea that you can have, and was had a while ago, and it's that one should be able to interpret your colored links as maps, right? So say that your link was the coloring of your link you associate to each of your components some vector space, some module, VA or VB. And then what you can sort of do is perform this isotopy that I've denoted over there, and look on the right-hand side and sort of squint and say, well, you know, since we have sort of arrows that are kind of colored by vector spaces, maybe we can turn this into some sort of map. And if you take the diagram we have on the right and read it from the bottom to the top, you know, you can kind of essentially, you can declare that, okay, we'll take this bottommost piece to be some map from C to, oh, sorry, there should be a little star, it should be tensor B, B dual over there. And then essentially decompose your tangle, your link into some set of elementary tangles, keeping track of you know, which maps you're composing with what. And then eventually at the top, kind of reaching back to something that's empty, to the space above, and interpret that as just a map from whatever you have back to the complex numbers, right? If you like this sort of diagram, I want to see many much better versions of it. They are actually in Campbell-Wheeler's thesis. He's done a couple of really lovely drawings like this for explicit computations for very nice knots. And so really what this boils down to, what we were talking about essentially, is an assignment of each of these elementary bits of this diagram we have on the right to certain maps between the vector spaces defined by you know, how we've colored each of these strands, right? And so this is a good candidate set for sort of the elementary tangles we'd need in order to generate any sort of any link, any framed link, right? And well, Reshetikhin and Turaev provide a very, very elegant way to do this. They give a very general way to do this, to give these prescriptions, but we won't need the full algebraic generality of it. We'll just look at a very particular case of it, and that case is for, well, it's for quantum SL2C, which we'll talk about in the next slide. But I'd like to also now, at this point, introduce some more protagonists to our story, and it's these quantities that are known as the quantum integer and the quantum factorial. And these are sort of relative to some primitive root of unity Q, where, you know, we've 2 pi over R, where R is some integer greater than or equal to 2. Okay. And these feature quite heavily in the construction of what's known as the colored Jones polynomial, a particular example of this prescription of taking bits of links and turning them into maps. And so with the notations R and Q as before, we look at the quantum group SL2C and its associated universal R matrix. So really what this is you know, U as a quantum group is some unital algebra over C with 4 generators that satisfy the relations given over here. And then for integers, well, for elements of the label set that we had before, remember the set 1 up to k plus 1, we define a basis for a bunch of little vector spaces. They'll end up being U modules. So for M, M is some label set. We define the mth vector space over here to essentially just be Cm, right? With basis labeled in this way. And there's sort of lots of early literature shows that, you know, you have this, one has a U action on these modules, and so you can think of it as U modules, right? And what this action then allows you to do is to look at the R matrix, which is this element of U tensor U. It's some enhanced Yang-Baxter operator that satisfies some other conditions. And well, what you can do is you can interpret this. Well, you can take this and see what isomorphism it induces on tensor products of these modules, right? And with respect to this basis we've defined over here, they have certain matrix elements, which I've written out in really gory detail over here. The theta is the Heaviside theta function that I just didn't want to have, equal to this if that, 0 if otherwise. Oh, I should mention S. S is Q square root of Q. I didn't write that down. But so there's an absolute abundance of these quantum factorials that we had over here. There's Q itself to the power of some polynomial, which we've defined down here, and a Kronecker delta function.
What is your reference scale that you want?
So this is, a lot of the computations are done in very nice detail in Kirby Melvin, Kirby Melvin's paper from 1991. I have a list of references at the end in case you want to check them out. But excuse me, this.
What is theta?
Theta. This is the Heaviside theta function. So it's 1 if the argument is greater than 0 and 0 otherwise. And well, that gives us the data from that essentially gives us the braiding isomorphisms we need, the maps we need to that we will turn the crossings in our diagram into. The other elementary tangles, you remember the cups and the caps and those little twists. Those are fairly easy to deal with. But really, the crux of this whole picture comes from the R matrices that pop out of this quantum SL2 picture. And well, taking the assignment that we had there for the R matrices and these other ones, these other maps that I've just mentioned, and feeding a link to it and seeing what pops out is what we take as the definition of the colored Jones polynomial, where lambda, the coloring is, like we said, a coloring of the components of your link by these U modules. And well, this is a map from C to C, and it turns out to be some nice polynomial, which you can very easily compute given a diagram of L. And so really what you can break your diagram up into some collection of bits. You can talk about, you have a bunch of edges. If you interpret, okay, well, technically speaking, you take the diagram, interpret it as some graph where the crossings are the vertices, and then take the edges of that associated graph together with the kinks, these little twists that we had, crossings, and the positive and negative caps and cups. And I essentially just set up some notation here. So edges and kinks, remember the original coloring of the strand they were from by lambda e and lambda phi. Kinks and crossings, remember the original orientation, whether they were a positive crossing that looked like that or a negative crossing which looked like that. And well, possible labelings of the edges by basis elements of the module that you've colored your strand by are given by the set B lambda, which if you B lambda E for every edge. And a crossing remembers the colors and labels of the strands involved by this tuple that we have down here, where the ordering comes from this diagram. And then essentially what the Recitic-Interaya function does when you feed it a link colored in this way is it spits out this quantity. Now the right hand side is dependent on your diagram. Of course, we've decomposed this into edges and crossings, and but they did a lot of work to show that this is actually this is actually good link invariant.
But the formula works only for R3 or also for some few manifolds?
So at the moment, this is the Cauchy-Jones polynomial just sitting aside. Yeah, R3, S3. Yes, so this is kind of the base case of the Jones polynomial. Okay, but a link invariant does not a three-manifold invariant make, and so you have to be quite careful when you start thinking about how do you turn this into a proper three-manifold invariant, and that will inevitably involve surgery descriptions. So what Ristich and Derived did to construct an honest-to-God three-manifold invariant is, well, in this case of quantum SL2, again taking some integer k, a non-negative integer k, together with r being k plus 2, the same label set, some manifold m, some link inside of m, and then additionally together with two links inside of S3 called LS and L0, which are both framed and oriented links, such that the tuple M and L, the manifold and the link that we want to compute an invariant for, is diffeomorphic to surgery on LS, it's the surgery link, inside of S3, together with L0 by an orientation-preserving diffeomorphism. And these LS and L0, they always exist and they're unique up to Kirby equivalence. And you also might want to color your link inside of your three manifold, which is the same story as before. And what they did, well, is they introduced a topological invariant for this tuple ML mu for every non-negative integer k, defined like this, with some prefactor, which I call alpha L of S, involving the signature of the linking matrix for your surgery link, together with a sum, essentially a weighted sum of colored Jones polynomials like we introduced before, where sort of the coloring lambda union mu corresponds to coloring the surgery link by lambda and the zero link by mu. Together with quantum integers corresponding to each of the labels, right? And the benefits of this is it's an actual computable complex number, which is great if you like to compute things. And well, what it means for this to be the mathematical model of Witten's description is, it's a little bit hand wavy given that the previous, the path integral isn't strictly defined, but they have all the same ingredients. They both produce generalizations of the Jones polynomial and arbitrary three manifolds together with this coloring. So we'll take it as the mathematical model for the Witten path integral. So if it's the mathematical model of this path integral, then some properties should carry over, right? And one of the properties you might immediately want to ask about is the large K asymptotics of this object. So for now, let's just consider closed-oriented three manifolds without a link inside of them. And well, we have a path integral on the top, which we call ZW, and we have our nice sum of weighted Jones polynomials, which we call Z. Now, so we have stationary points of our path integral. These are the classical solutions to this to your action, which in our case they correspond to flat connections, which I've denoted as living in some space of equivalence classes of flat connections called M flat. And as you send k to infinity, one would expect that you should be able to make stationary phase arguments, and that what comes out of the path integral is essentially a sum over these saddles, a weighted sum over the of saddles, with one sort of term corresponding to each of the Chern-Simons invariants of these flat connections, perhaps with some Poisson series in negative fractional powers of R attached to each of them. And this is sort of a very standard thing to do when you're dealing with path integrals. But what about for Z? What about for our quantum groups description? The behavior there is a lot less clear. As you send R to infinity, or equivalently K to infinity, you have to deal with a coloring label set, this summation, having more and more terms. You're evaluating these Jones polynomials using colors that are, also growing. You're evaluating them closer to 1. And if you remember the formula for the colored Jones polynomial I showed on the other page involving edges and diagrams, there's a lot of stuff going on there. And it's really not clear what the asymptotics are of this quantity of Z at first glance. But the asymptotic expansion conjecture for closed-oriented 3 manifolds says that, yeah, we should expect this behavior as well from Z in general. There have been some important cases that have been proven. It's open in general, but certain specific cases have shown to hold. Back in 1992, it was Lisa Jeffrey who showed that it was that this holds for lens spaces and torus bundles. That's the Z of these has these nice predicted asymptotics. Charles and Marché in 2011 showed that when you do Dane fillings of certain Dane fillings of the figure 8 knot, you get what the conjecture claims. Andersen and collaborators looked at finite order mapping tori. Actually, Andersen and Mistegård also looked at mapping tori for some classes of diffeomorphisms. And then very recently, in the case of ciphered fibered integral homology spheres, this was proven by my host here in Paris for the next 2 months, David Sauzan, together with my supervisors back home, Andersen and Mistegård, together with collaborators Han, Lee, and Sun. And this was based on some more work done in the late 90s by Lawrence and Rosansky, which looked at similar things. And so we're still a little bit far away from proving this conjecture in general. But in what follows, I'll present some steps to try and start teasing out this expected behavior from these invariants, right? And that involves taking these nice sums that we have and turning them into integrals. So pretty much ever since people have started using the residue theorem, they've used it to take sums and spin them up into integrals, which are easier to compute for whatever reason. So, I mean, this is essentially just the definition of, well, this is just the residue theorem, right? I'm not going to go into too much detail over here. But when you have some summation, what you can do is, provided you can come up with some polymorphic extension of your summands on the left-hand side, what you do is you affix to it what I call a pole machine, whose only purpose in life is to just generate poles at certain points in the complex plane, and then you perform an integral around it, and then you should just get back what you get on the left-hand side. The benefit being that the right-hand side is often more amenable to asymptotic analysis. You can do crazy things like deforming contours, stationary phase, all that good stuff. And yes, it's a great tool for studying the asymptotic properties of sums, but only provided you can come up with a polymorphic extension of your summand. And the way we do that in our case is by this magic function known as Faddeev's quantum dilogarithm. So it has some little parameter gamma that's bigger than 0, and some initial domain of definition. The complex plane, that's kind of this strip. And what you can do is on that strip, you can define the holomorphic function given over here, by epsilon is some little parameter as well. And what you can show, and indeed what Faddeev did, was that for complex zeta with zeta kind of in a slightly smaller strip, zeta plus and minus this little parameter also lies within this initial domain, and in fact, this function satisfies this very nice functional relation. And that essentially allows you to bootstrap your way out of this initial domain, analytically continue it with poles and zeros, but nonetheless a meromorphic function on the entire complex plane. What we'll be working with is a slightly different normalization, pre-multiplied by some exponential, and then feeding the dialogue some other argument. Really, in your mind, you should think that our small parameter over here is pi over r, 1 over r, or pi over r. So it's a bit of a gross statement, but essentially what you can show is that it has poles at all simple poles at on some semi-lattice, I guess, and simple zeros on some other one. And well, what this does for us is it provides a meromorphic extension for our quantum factorial. If I were to cover the right-hand most side of this equation, you could tell me, and look, well, if you looked at the middle and I told you that I wanted m to be not an integer, you'd tell me I was crazy. But the right-hand side works, and so we suddenly have the meromorphic extension that we need.
Sorry, in your normalization, all the zeros and poles are real?
So R can be complex, actually. Yes. Yeah. But yes, in the case of real R, it's and well, it's at this point I'll recall our R matrix coefficients that I remarked were just full of quantum factorials. And well, with this Faddeev dialogue in hand, what we do is we spin up a meromorphic extension of it, right? We define this polynomial in 4x variables, which correspond essentially to the labelings of the four strands at a particular crossing of your diagram, together with y1 and y2, which are the colors of those two strands. Yes, we define this polynomial in Q. We define, also using the quantum dilogarithm, something like a holomorphic Kronecker delta function, which is 1 when the argument is 0, but is 0 when the argument is an integer, a non-zero integer, right? And we take those and define this big R function, which is the quotient of these Faddeev dialogues, together with an exponential of our polynomial and this holomorphic Kronecker delta. And what we show, it's quite simple using the relation, the functional equation I showed on the previous slide, is that for all of your labels and all possible basis elements, this function agrees with the R matrix coefficients above. So okay, we're part of the way there in order to being able to rewrite the Color-Jones polynomial as an integral. And indeed, so I've recalled the overall formula over here just to remind you where these R matrix coefficients come from. And so let's turn the right-hand side into an integral, right? We define RD to be essentially just a very obvious meromorphic extension of this sum end, given what we know now. We define chi to be that thing with a pole machine attached to it that will produce the right residues when we integrate over a contour, which we define over here, which is essentially just a collection of pillbox contours that encircle the poles that we need in order to obtain the summation that we have on the top. And then with that in hand, it's just one makes a pairing of this contour together with this meromorphic form. Residue theorem applies, and essentially when you feed it some proper coloring from your coloring set, this J twiddle, this integral, you recover the Color-Jones polynomial. And I mean, you wrestle a little bit with sort of seeing how big your pillbox contours can be in order that they don't bump into poles coming from sort of other poles from these cotangents, and also the other poles from the Faddeev dialogues. But luckily, those are far enough away from one's pillbox contour that you don't have to worry about them. And the residue theorem can be applied very trivially just to obtain this result. So that's an integral formula for the color-Jones polynomial. Let's try the same thing for the WRT invariant, which is arguably an even simpler sum now that we have this integral formula for the color-Jones polynomial, because there are no quantum factorials. We don't need to worry about Faddeev dialogues. And so we similarly define a meromorphic form, which involves this framing correction that we had out front, this alpha, together with the meromorphic form from the previous slide, holding the coloring of your second link fixed to this prescribed mu, and then again affixing a pole machine that gives us the residues we need, and this sine yp of r divided by sine pi over r is what produces this product over the quantum integers of the colors. And then again, you define your integration contours. There's a slight subtlety when it comes to this J twiddle, this integral for the color-Jones polynomial. It's not a meromorphic function of the color. And this is simply just because if you sort of continuously change the color from one value to the next, or one integer to the next, what you're doing by doing that is you're increasing the size of your pillbox contour. But at some point, you will bump into the other poles coming from the cotangents. So there are some regions, there are some values for which depend on epsilon and sort of how far your pillbox contour, how thick it is. There's some values for which J twiddle is discontinuous, and you can fill in those gaps, but what you end up with is not a continuous function. So unfortunately, the integral that we have to perform over here in order to apply the residue theorem isn't a nice pillbox contour over 1 all the way up to k plus 1. Instead, it's a union of little circles around each of the integers, where epsilon is just some small number. But with that contour and that meromorphic form in hand, we just perform the integration and obtain an entirely analogous result. And that is that this z twiddle quantity, when evaluated at some proper coloring of your L0, gives you the WRT invariant of that triple. Okay, so what was the point of all of this? The point of all of this was to spin the sum up into an integral and then hopefully do something cool with it. Really the whole motivation here is to study the semiclassical behavior. How do we manipulate this integral now? And to do that, we're going to look at the semiclassical properties of Faddeev's quantum dilogarithm, right? Which has been shown by many people to be governed by the classical Euler dilogarithm, right, to leading order. It's the exponential of 1 over 2i gamma of this Euler dilogarithm plus some extra stuff which I've called E. I'm sweeping a lot under the carpet over here. E is actually, when you do your proper asymptotics and take gamma to 0, you end up with an entire resurgence story. A lot has been written about that by many people, some of them here today. But for now, we'll kind of fall back on the results of Andersen and Hindson in 2005, who used it in the case of examining the figure 8 knot. And what they showed is that E, at least in the region of the complex plane that we are interested in, i.e. around these kind of pillboxes, is well bounded. You can establish bounds, but they are you can think of it as being of a lower order in this small parameter gamma. And so using this, taking this quantum dialogue and approximating it by the exponential of a classical dialogue it's been a handy tool for ages. Back in 1996, it was Kashev who showed that the Kashev invariants of some hyperbolic knots over here, they ought to be governed by their volumes, right? And this idea sort of came from the fact that a lot of the hyperbolic volumes that appear in the literature, sort of the associated gluing equations, all involve these similar types of dilogarithms. And indeed, one shows using quite a similar trick, taking the Kashev invariant, turning it into an integral, and then just doing it's a very elegant analysis, just looking at the critical points of this integral in some semiclassical limit, and essentially just showing that yes, these are on the nose equal to the hyperbolic volumes of those knots. Like I mentioned, Andersen and Hindson looked at 4.1 in a little more analytic detail and got some error bounds. And of course, the Faddeev dialogue is really, really key to the whole Andersen-Kashev TQFT story, which I won't talk about too much over here. But yes, like I said, the full analytic story requires resurgence, and that's a line of inquiry that will hopefully be exploited by us in the not too distant future. So, how do we use this semiclassical approximation? I'm sorry, this is the full formula. I'm only going to show it once because it's terrible. But the integrand of our z-twiddle integral modulo, without the pole machines, is given by this product over crossings multiplied by this exponential, which is some polynomial in the y and x variables. How do we do semiclassical analysis on this? Well, it's instructive to rescale our variables by this large parameter. So send y and x to ry and rx. And then once you do that and use the semiclassical approximation that we talked about on the previous slide for the Faddeev dialogue, and do lots of algebra and rearrange lots of things, it turns out you can package all of the terms in the exponential that sort of grow with that have a prefactor of r into what we call the semiclassical phase function, which is this phi over here. I've written out explicitly what phi is. There's a contribution to phi that comes from the framing of your link, together with one contribution that comes from every crossing of your diagram. And every crossing is itself has a degree 2 polynomial part. In fact, it's a purely quadratic polynomial. There are no linear terms in here, together with some sum of these dilogarithms of exponentials of sort of various variables associated to each of your crossings. And you might go, okay, great. This is what do we do with this now? But you can take a look at this and try some basic examples and try and solve for the critical locus of these. It's really difficult because you've got one x coordinate for every edge, and of course one y coordinate for every component of your link. So even doing something like the trefoil is already like a 7-dimensional integral. But it actually buys us quite a lot by packaging it in this form. Because it then allows us to ask another question. How close are the critical values of this phase function that have popped out? How close are they to the SU2 Chern-Simons invariance of flat connections on your manifold? Because ideally, that's really what we'd want. This is kind of what pops out of the path integral description too. That stationary points correspond to the Chern-Simons invariance of these flat connections. Well, one way to answer this follow-up question was talked about in a paper by Sökbom Yoon in 2018, based on work by Garfalidis, Thurston, and Zickert, that involves computing SL2C Chern-Simons invariance for some description of your manifold. And what Yoon did was he looked at computing these directly from the diagram of your surgery link. And it's a slightly different setup than us. One, again, associates one variable to each component of your link, and then one variable to every component, every region of your diagram. If you think of drawing a link diagram and looking how it divides the plane up into some number of regions, the unknot would divide it up into 2 regions. You associate some complex variable u to each of those regions. And then through some very technical machinery, Yoon defines what's known as what he calls the generalized potential function on this space of all of these variables. And this is a squashed version of 2 theorems from Yoon's paper. And it's that corresponding to certain points inside of this space, which he calls non-degenerate solutions, one can construct representations of your fundamental group of your manifold, or PSL2C representations, with certain holonomy conditions that are described that involve this y coordinate. I can talk more about this if you need, but for now, it's essentially saying that there are kind of distinguished points in the space that from which you can compute some representation, and moreover, that this generalized potential that he constructs, when this representation that you find as an SL2C lifting is given by, the value of this is actually the complex volume of your representation. And so, how this relates back to us is that essentially, once you pull back to sort of these edge coordinates instead of these region coordinates, what you find is that this overall potential function agrees with our semiclassical phase function on its critical locus up to some degree 2 polynomial. There's some tiny discrepancy there. All of the dilogarithms are there. A large chunk of the degree 2 polynomial bit is also there. There's just this little discrepancy. I mean, this is kind of my current task. It's what's keeping me up at night. So we're working pretty hard to try and shave this discrepancy down, or to do some proper analysis to see if there's contributions that come from elsewhere that are confusing the story a little bit. But it seems to be one seems to be going in something of the right direction. And well, that's about all I had to say. So here's what the title promises: WRT invariants as finite dimensional integrals. There's an integral. And in the particular case, when your link is empty, actually you can do it when your link is non-empty as well, but essentially when you rescale your variables, you end up with some phase function that, from what we can tell, is quite close to the SU2 Chern-Simons invariance, and where we've packaged all of the Paul machine and other contributions up in this little function that I call f. Again, lots swept under the rug over there. But then there's also this question about, there's also noticing that these are integrals over middle dimensional cycles, which lays perhaps a good foundation for sort of a full-blown resurgent analysis. So we have lots and lots of questions then about how one decomposes these compact cycles, these pillbox cycles into Lefschetz thimbles, how these interact with the other poles of the quantum dilogarithm that are lying sort of further out in the complex plane. I think whether this final bit of the story makes it into the next preprint or the following one, I guess you'll have to wait and see. It'll be in my thesis, but time will tell. It always does, I guess. And with that, I'll say thanks.
Thank you very much. And are there any questions or comments? Maybe going back to the slide when you said there is this alternative mismatch on the actual the Chern-Simon the critical point and the one from the function you find. But are there any examples somehow in which you don't have this mismatch, or for instance, if you don't have this CF, like you have the volume plus an extra term?
Right. So, I mean, if we were looking at SU2 representations, then the volume shouldn't be there. I mean, it should be 0. Look, when you don't have any crossings in your diagram, if you're doing something very, very basic like the framed unknot, which will give you LF1 lens spaces, I think, which is already a done deal. That was done in 1992. But when you plug in that, then you sort of have some agreements with what we have. It's these crossing functions sorry, say again.
It should come from the Faddeev.
Well, I mean, in that case, there's not really any Faddeevs.
I mean, so if
yes.
So when you have this mismatch, it's probably due to the Faddeev.
Yeah. So there are lots of contributions that we think we might have to bring into the fold to get a fuller picture. One is seriously dealing with the multi-valuedness of this Euler dilogarithm. The other one is actually the pole machines themselves. You can sometimes, because remember, when you're doing your rescaling, you're also rescaling the pole machine. So one should also, and if this is some cotangent type thing, one should also expect contributions to this phase function. The holomorphic delta function that I mentioned also might contribute, but from what we saw, all of these they contribute kind of linear discrepancies, things that are linear in the variables. So it doesn't quite solve the quadratic bit. That's still a bit of a mystery. Yeah.
Okay. Thank you. Online, someone has other question from Zoom?
I don't see anything in the chat.
So here, what is satisfactory is that your function capital phi reproduces the Chern-Simon's SL2C Chern-Simon's value when you look at the critical values. Nearly, but well, hopefully. But then you have the further problem of eliminating the non-SU2.
Yes. Yeah, exactly.
From values from among SL2C, you must eliminate some of them.
Yeah.
Any clue as to, because in the final asymptotic result, you should not see.
Yeah, you should not see SL2C. Well, you shouldn't see non-unitary ones at all.
Any clue about that?
Not at the moment. Not at the moment. That's something I'm also thinking about.
That's a good preliminary step. That the Seifert story with Andersen and they had initially something in which potentially all SL2C connections would contribute, but in the end, by some miracle, only SU2 survived.
Yeah, that'll have to do. That also plays with sort of the eventual question of how you do this Lefschetz decomposition of these cycles. Maybe it's the Lefschetz symbols that are sort of associated to these unitary critical points that are sort of the ones that survive, but we'll see.
If there are no other questions or comments, let's thank Sam again. And we will resume at 45.